Okay, in this video, I'm going to go to the AQA A-level Chemistry Paper, paper 2, and this is from 2021. I'll do the first half in this video and finish the second half in the next. Okay, so the first question is about triglycerides. Okay, coconut oil contains a triester with 3 identical R groups, and the triester reacts with potassium hydroxide. So this is alkaline hydrolysis of an ester, actually to make this stuff, which is of course soap. I think they're going to ask about that. They are, so the salts of carboxylic acids, long chain carboxylic acids, are soap molecules. Complete the equation by drawing the structure of the other product of the reaction in the box. Okay, so the other product you're going to get, of course, is going to be this bit here. You're going to split those ester linkages, which is glycerol. So that's going to be like that. Sorry, that's wrong there. One hydrogen there. Okay, so you get the triol. Right. Right. Name the type of compound shown by the formula like that. Well, that is it's a salt, carboxylic acid salt, and what's it used for? It's used as for soap. Okay, so we just want to draw that a little bit more. What's that really? It's a carboxylic acid. You've removed the proton from the acid group, from the OH group there, and you've got a K plus ion as well. Okay, so that's a potassium salt of a carboxylic acid. Okay, the triester in coconut oil has a relative molecular mass of 638. In the equation, so R represents an alkyl group that can be written like that. So CH3, CH2, CH2, blah, blah, blah. Now we've got to work out the value of N in that thing. Okay, so how are we going to do that? Right, so we know that the MR of the whole thing is 638. All right, so let's work out, we want to work out what the MR of R, the R bits are. So we've got to work out what the rest of it is then. So that's CH2 there, that's going to be CH2, that's going to weigh 14, 12 for the carbon then, yeah, 2 for the hydrogens. That bit's going to be 13, CH, another CH2, that's going to be 14. Each of those, of the carbon and 2 oxygens, that's 12 plus 16 plus 16, that's 44. So we're going to have that time, so 44 there as well, 44 there. Right, if we add that lot up, what do we get? So we've got 3 times 44. 3 times 44. We've got 2 14s. And we've got a 13 as well. That all comes to 173. Okay, so now we've got to subtract that from 638, and that will tell us what the R's are. So how many R's we've got there? We've got 3R. So I'm going to 3R, that weighs 638 minus the bits we've accounted for there, the 173. So 3R is equal to 465. So R is equal to divide 465 by 3, gives you 155 for that. Okay. Right. Now we know, so we know each R group weighs 155. We know that each CH2 weighs 14. Right. So let's see how many times 14 goes into 155. 155 divided by 14. That is it's going to be 11 and a bit. Right, just over 11. Now, the reason why it's not an exact number, of course, is because for this R group, the R is CH3, CH2, N. So it's got a, and so it's got a CH3 there, which weighs 15. Okay, so let's do N. So let's do 155 minus 15. That gives us 140. Okay, so how many times does N go into 114? That weighs 14. How many times does that go into 140? Well, it goes 10 times. N is equal to 10. Okay, so the answer is the value of N is 10. Okay, so we've got some coconut oil is heated with KOH in aqueous ethanol until it's all hydrolyzed. The mixture is cooled and the remaining KOH left over. Okay, you find out how many moles you've got by doing a titration with hydrochloric acid there. Okay, so we've got to calculate the percentage mass of the triester. Right, now how are we going to do that? So what I'm going to say is let's start off, let's find out the initial, what we've got to do really here is we've got to say, we've got to find the moles of KOH which have reacted. And from the other equation, we know that 1 mole of oil reacts with 3 moles of KOH. Okay, so we can find out the moles of KOH reacted, divide it by 3. That will give you the moles of the oil. Yeah. If we know the moles of the oil, we can then, because we know the MR of the oil, it tells us it's 638, we can find out the mass of the oil. So that's the approach we're going to take. Right, so let's start off then, moles of KOH to start off with, and I'm going to call that KOH initial. Call it I for initial. That's equal to mass over MR. We've got 1.41 gram, 1.45 grams. The MR of KOH, that's going to be 39.1 for the potassium plus 17. That is, what is it? It is going to be 56.1. So 1.45 divided by 56.1. That gives us 7.504 times 10 to the minus 3. Right, that's the initial moles of KOH. Okay. We're going to need that later on. Now let's work out the final moles of KOH. And how are we going to do that? Okay, now we know that KOH reacts with HCl in a 1-to-1 ratio. Okay, and they're doing a titration there. So that will give you KCl and water, of course. Okay, the important thing we need to worry about though, it's a 1-to-1 ratio. So can we work up the moles of hydrochloric acid? Let's do that. Go over here a bit. Okay, so moles of hydrochloric acid is equal to concentration times volume. The concentration is 0.1 and the volume was 15.65 centimeters cubed divided by 1,000. We need the volume dm cubed. That gives us 5.65, sorry, 1.565 times 10 to the minus 3. And we said that the HCl and the KOH react in a 1-to-1 ratio. So we can say therefore the moles of KOH at the end, it's called KOH final, is going to be the same as that. 1.565 times 10 to the minus 3. Okay. Now we need to work out the moles of KOH used up, which is going to be moles of KOH used is going to be equal to the KOH initial moles, which we worked out earlier, minus KOH at the end, final, which we've worked out just now. Now, the initial moles of KOH we worked out in the earlier calculation, that was 7.504 times 10 to the minus 3. And we just worked out what that is, 1.565 times 10 to the minus 3. That gives us 5.939 times 10 to the minus 3. Okay, that's the moles of KOH used up. Now we know that 1 mole of the oil reacts with 3 moles of KOH. So the moles of the oil left over, sorry, the moles of the oil which reacted is going to be 5.939 times 10 to the minus 3 divided by 3, which gives us 1.979 times 10 to the minus 3. That's the moles of the oil. So finally, we now got to work out the mass of the oil. So the mass of the oil is equal to moles times MR. (1.979) times 10 to the minus 3. And the MR of the oil, they tell us, was 638, which is equal to 1.263 grams. Okay, so we need to work out the percentage purity of the oil. So percentage purity of the oil, or how much of the, what percentage it is it of the stuff was the coconut oil. So that's equal to the mass of the oil divided by the total mass times 100. Well, we worked out the mass of the oil was that 1.263. And the total mass they started off with was 1.450. And that works out as a percentage to be 87.1. There's 3 significant figures. So that's how you can do that one. Quite an unusual calculation. It's like a back titration, really. Okay, quite unusual for that to be in an organic chemistry paper. Okay, right. Secondly, number 1.4. Right, suggest why ethanol is a suitable solvent when heating the coconut oil with KOH. Okay, now why is ethanol going to be good? Well, you can't use water because coconut oil won't be soluble in water because it's pretty hydrophobic. It hasn't got many polar groups in it. So ethanol, the reason why we're using ethanol is because it will dissolve the oil and also KOH. So ethanol is a solvent. It's got polar properties and also non-polar properties. So it will dissolve polar things like the KOH, but it will also dissolve non-polar things like the coconut oil. I think all you need to say is that what I've written there in blue for that one mark. Give a safety precaution used when heating the mixture. I would probably say, right, you're heating ethanol, which is flammable. So you would use an electrical heater. Why would you do that? Ethanol is flammable. Okay, right, that fairly straightforward. Right. Question about fuels. This is right. Right. The petrol fraction obtained from crude oil can be used as fuel in cars. The meaning of the term fraction here, what do we mean? Well, is petrol a pure substance? Is any fraction from crude oil a pure substance? No, it's not. But what you can say is all the molecules in a fraction are going to have similar boiling points. So it's a mixture of molecules with similar boiling points. Hydrocarbons, let's say. Similar boiling points. Okay, hexadecane can be cracked at high temperatures to form petrol. Complete the equation shows cracking to show hexane and cyclopentane only. Well, what's the formula of hexane? Well, hexane is a saturated hydrocarbon, so it's going to be CnH2n plus 2. Hex, so that's going to be C6H14. And cyclopentane, well, because it's cyclopentane, the general formula, it isn't plus 2, is it? Cn just H2n. So that's going to be C5H10. And we've got to balance that. Well, you can see, yeah, to balance that, we're going to have to put a 2 in front of the cyclopentane. Right, that's quite important to remember that. Look, if you've got CnH2n, it either means the molecule has got a double bond in it or it's cyclic. Right, the name of the catalyst, what kind of cracking is that? Well, that is not thermal cracking because you're forming these cyclic molecules. So it's catalytic cracking. So it's going to be a zeolite catalyst. Right, see, this is an unusual question. I don't think they've ever asked this one before. And you got to have a look at the mark scheme, really. Carbon dioxide is give a reason why carbon dioxide absorbs infrared radiation. Right, now, I would say is because when the bonds will absorb a certain amount of energy, and that energy, using the equation E is equal to hf, Planck's constant, is in the means of the F, the frequency is in the infrared region. If you look at the mark scheme, I think the easiest way of putting that, they say, is that the infrared radiation has the same frequency as the frequency of bond vibration. That's the quickest way of saying it. If you look what the other bits of the mark scheme, you can say basically what I say, but that's much more verbose. Okay, so I would probably just remember that if they're going to ask that question again. Okay, compound Z, okay, which is, we've got an alcohol group and an NH2 group there. Okay, amine and an alcohol group can be used to remove carbon dioxide from waste gases produced in power stations. Shows a suggested mechanism of the reaction of Z with CO2. Okay, so we've got nuclear. Obviously you've got a delta positive on that carbon there, and you've got nucleophilic attack by the amine onto it. You form that intermediate, and that's going to lose one of those protons, and it's actually this NH2 which removes the proton. Oh, what's happening there? I'll just draw it. So if you wanted to draw a curly arrow, it doesn't ask you to do this, but what's happening is that curly arrow is picking up that H plus there, and this bond breaks, and that pair of electrons goes back into the nitrogen. So the nitrogen is no longer has there's the nitrogen there, no longer has got a positive charge on it. Okay. Oh, it does actually that. Draw two curly arrows to complete the mechanism figure 1. Yeah, it's those two which I've drawn there. And deduce the role of Z in step 2. Well, what is it doing? Z, this stuff here, it is accepting a proton. What does that mean? It is a base. It is acting as a base. Okay, so now onto shapes of molecules. So you can represent the amine as that, yeah. And you can represent the protonated thing like that. Draw the shape of those two things. Right, now we've got to remember really, nitrogen and this one here, nitrogen's got 5 electrons in its outer shell, so it's going to be forming, if you think about it, it's going to be forming, here's nitrogen, let's just draw it. It's going to be 3 covalent bonds. I've only drawn 3 dots there for the nitrogen's 5 electrons from group 5. So it's going to have a lone pair there, okay? So we've got this one here, we've got 3 bond pairs and 1 lone pair. So it's basically the shape of ammonia. So how are we going to draw that? There's one coming out of the plane of the molecule there. We've got X. And we've got an H in the plane of the molecule, and we have got the lone pair there. Right, that's what it is. So we've drawn the shape. What is the shape called? You call that trigonal pyramidal. Now, what's happening with this one here, this one, right? It's protonated, okay? So we've got an extra H plus on there, and the H becomes H plus. So now what's this has got? This hasn't got 3 bond pairs, 1 lone pair. It's got 4 bond pairs, which is, of course, is just tetrahedral, like methane. So I draw that like that. The plus on it. And right, you'd call that tetrahedral, that shape. What's the tetrahedral bond angle? Is 109.5 degrees. Now it's asking us, was the bond angle, which was the bond angle the biggest, in the red thing or the green thing? Well, it's biggest in the green thing, isn't it? Because what happens to that bond angle there, in the red one, it gets squashed because this lone pair sort of pushes it down. Usually to people quote that as 107.5. And so the how would you explain that answer? I would say that the red thing has got a lone pair. Lone pair bond pair repulsion is greater because that makes the bond angle smaller. So I would say, definitely say that lone pair bond pair repulsion is bigger than bond pair repulsion. Okay, bioethanol is used as an alternative to fossil fuels. Okay, this is a 6-marker question. A statement appeared on the website. The fact that bioethanol is carbon neutral outweighs the environmental disadvantages of producing bioethanol. Right, evaluate the statement. You've got to remember this is a chemistry exam. It's not a biology exam or a geography exam. So you do biology, you have to be a little bit careful about going on too much about the environment and habitats and stuff. We need to concentrate on the chemistry. In your answer, you should include an outline of how bioethanol is produced, okay? And relevant equations, those 2 points. So let's have a think about that. Right, let's think first of all how bioethanol is produced. Well, first of all, you need photosynthesis. So you're going to have 6 carbon dioxides and 6 waters in photosynthesis goes to make glucose and oxygen. And then what happens is you get, so that's photosynthesis. Next thing, you need fermentation to occur with yeast. And you get glucose goes to ethanol and carbon dioxide. How are we going to balance that equation? Well, you've got 6 carbons on the left, you've only got 3 on the right. So put a 2 in front of the ethanol, a 2 in front of the carbon dioxide. Okay, and that will do it. Fermentation, right. So that's how you make ethanol. Probably a good idea to say at that point that the ethanol is not pure. It will only be about 15% in an aqueous solution. The rest of that is mostly water. So to get ethanol from that, you need to carry out fractional distillation, which of course is going to require you to heat it up. So that's going to use energy. So that's going to generate carbon dioxide usually when you however you heat it up. So it's not really carbon neutral due to that alone. We'll talk about other reasons why it's not 100% carbon neutral. Let's talk about when you burn the ethanol then. Right, you burn ethanol, and because we've made 2 moles of ethanol, I'm going to actually put 2 moles down the equation there too. So this is like, if you like, this is coming from 1 glucose plus oxygen. You're going to get carbon dioxide. Obviously, going to be 4 carbon dioxides. Now you're going to get water. How many waters? Well, we have got 12, so it's going to be 6 waters. We've got 12 hydrogens on the left, so it's going to be 6 waters. So that means we're going to need, to make that total, we need 6 oxygens there. Right, now the reason why they're saying this is carbon neutral is because, look, when you made 1 molecule of glucose, you used up 6 molecules of carbon dioxide. And when you use that as a fuel, well, you're going to make 4 molecules of carbon dioxide there, and you will have given 2 off in the fermentation as well. So that's equal to 6 carbon dioxide, which is the same amount of carbon dioxide taken in by the plant to make the molecule of glucose. So that's why people would say it is carbon neutral. We've got to say now, so why isn't it really carbon neutral? We said, first of all, this bit here, you've got to carry out fractional distillation. I would probably also mention that you've got, when you generate CO2, when you grow the crop, you've got to put fertilizers in and so forth. That uses energy. You've got to have machinery to plant the crop, harvest the crop, and then you need transport of the stuff, and that generates CO2. So it's not really carbon neutral. And an analysis of environmental impacts. Okay, as I say, this is a bit careful. It's a chemistry exam, it's not biology. So I looked in the mark scheme, and they do say mention deforestation and lack of biodiversity. You're growing a monoculture crop, and that reduces the amount of other living things that would otherwise be taking up that space. But I don't waste time saying that. You've got most of your 6 marks by talking about the chemistry there of those equations. Okay, 3.1. Seem to have lost a little diagram here, which I'll just tell you what it is. Okay, so right, 3.1, question 3.1 is about finding the enthalpy of combustion of hexane. So that's heptane, I think it was actually. Doesn't really matter. Using the apparatus, so you had a copper can, which is clamped there with some water in it and a thermometer. And here you have a spirit burner, right? And you've got your hexane in there, heptane in there. Okay, so it said draw a results table that you would need in order to be able to work out delta HC for that. Okay, So to work out delta HC, we're going to have to use two equations. We need Q is equal to MC delta T. So we're going to have to measure the temperature change of the water in there, first of all. So we're going to have one table where we will have temperature, degrees C. Now you need to measure delta T, so you will need to measure the initial temperature of the water and the final temperature also. Okay, what else will you need to measure, record? Well, after we've got Q is equal to MC delta T, then we need to, delta H combustion is going to be Q over the moles of hexane burnt. So we need to know how many moles of hexane burnt. How are you going to work that out? We need to work out the mass of hexane burnt. Hexane, keep saying hexane. So what would you need there? You need a very similar table. You'd want initial mass of the burner, and you'd want the final mass of the burner, and that should be measured in grams. Okay, and you find out the mass that you've used there by subtracting. And we had that as a mock exam question in my school, and people answered. It's a really easy question, but people just read too much into it, and they didn't get these two tables at all. They started saying, "Oh, measure the temperature in degrees C every minute." So we don't need to do that. You need to initial temperature, final temperature, and you do need to know the mass of the heptane burnt as well. So that's all you need to do for that. It was quite an unusual question, really. Not difficult, but just unusual. Right. 3.3 suggests two reasons. This is very standing. While the enthalpy of combustion, state two disadvantages of using a glass beaker on a tripod and cause. What did they use? They used this, which is a copper calorimeter. Disadvantages, right? So a glass beaker has got a higher heat capacity than copper. So that means a lot of the heat is going to go into heating up the glass and not heating up the water. And that's going to make things inaccurate. Also, if you had a tripod, if you put the beaker on top of the tripod, then and the gauze, it's going to be too far from the flame. And so a lot more heat energy is going to be lost into the air rather than going into the water where you want it to go. So the two best suggestions there, I think. Okay, right. Question 3, this is an extremely standard question, isn't it? Two reasons why the value of enthalpy of combustion are less exothermic than the data book value. Of course, they are heat loss to the surroundings and incomplete combustion of the heptane. Always ask that question. Of those two, I think the heat loss to the environment is far more significant than the incomplete combustion. Right. One addition to the apparatus that would improve the accuracy, again, a very standard question, is I would say probably put a lid on the copper calorimeter, or put insulation around the copper calorimeter. Not, as a lot of people said, do it in a polystyrene beaker, because of course that would just catch fire and melt. Okay, insulate the copper can or put a lid on it to reduce heat losses. Okay, on to a question about benzene. Okay, so we've got the K-Coulé structure with the alternate single double bonds here, and we've got the structure which we show here, shown with delocalized electrons. And we've got figure 3, which is a sort of a kind of diagram, a Hess's law sort of diagram to show the relationship there. Now, what we're going to do, we've got use figure 3 and the data in the table 1, which is on the right there, to calculate delta H2. So we want to find out that value of delta H2. Let's just think about what we're doing there first of all. Right, so it is saying, look, the enthalpy of formation of benzene, right? It is there, it is slightly endothermic, right? But you would expect it to be a lot more endothermic all the way up to there if it was the alternate single double bond structure. So that means benzene is the delocalized structure is more stable. Okay, you don't have to put as much energy to form it as you do with the K-Kool-Aid structure. All right, let's now we just thought about that. Let's do the calculation bits that we're going to have to do. Okay, so delta 8, let's think about this arrow here. This, we can do that in red. What we're doing there is we are breaking 3 double bonds, and they've got a value each of 612. So, and that's endothermic, so 3 times 612. We're breaking 3 carbon-carbon single bonds. That's 3 times 348. And we're also breaking 6 carbon-hydrogen bonds. Carbon-hydrogen bonds, they have got 412. So if you add that lot up together, you get if you add that lot up together, you get 5,352. Okay, now let's have a think about this arrow here. I'll draw it in blue. What we're doing there? Well, we're starting off with solid carbon. We're atomizing 6 moles of carbon. So that is going to be 6 times 715. And we are also atomizing, well, we have to be careful here. Look, we're forming 6 moles of gaseous hydrogen. So that is 6 times the atomization of hydrogen, not 3 times. The definition of atomization is the enthalpy change when you produce 1 mole of gaseous atom. So it's 6 times that value. Right. Add that lot up together. What do we get? We get 5598. Okay, and we know they tell us this this one here. Tell us what that is. Delta H1. So we can see that delta H. You can see the green. If you look at this side, so the red value 5352 plus the green, which they tell us is plus 83. Plus delta H2, which we don't know what that is. Delta H2, and that's what we've got to find out, is equal to this blue value here, 5598. You can see that from the diagram. So let's rearrange that. Delta H2 is equal to 5598 minus 532. 5352 minus 83. That gives us 163 kilojoules. Okay, now we have to decide what is the sign of that. And how do we do that? We'll look at the arrow. The arrow is going up. Anything going up is endothermic. So the sign is positive, 163 kilojoules per mole. So basically, the K-Kool-Aid structure is 163 kilojoules more stable than you'd expect it to be if it was alternate single double bonds. Right. The next question is, why is it more stable? Which is okay. Explain in terms of structure and bonding why the K-Kool-Aid structure, is more stable than theoretically what that one is. And it is because you have got delocalization of electrons. And it says the mark scheme, you can put pi in, you don't have to have that. And if you think of why is that going to make it more stable is, which you don't have to explain, just one mark, that's all you have to say, but why is it more stable? Well, here you've got 3 regions of high electron density, okay? Now, electrons don't like being shoved into, and they repel each other into the same small space. And so if you can spread them, instead of spreading over the 3 regions into over, well, that's essentially between 3 carbon bond lengths. Here, they're spread over 6 carbon bond lengths. So it's going to be, the electrons don't repel as much and so it is more stable. Right, now we are on to mechanism question. Okay, this is the nitration of benzene using concentrated nitric and concentrated sulfuric acid. And figure 4 shows the incomplete mechanism. Right, name the mechanism. Of course, this mechanism is always electrophilic substitution. Okay, this is a little bit different than usual. We've got to complete the curly arrows in figure 4 because they've asked to show the curly arrows in the formation of the electrophile, which we don't normally show. They just ask for an equation for that, and the equation for that would usually say is, right, you get nitric acid and sulfuric acid. The sulfuric acid acts as an acid and protonates the nitric acid, so you get H2NO3 plus and HSO4 minus, because that's lost a proton. And then what happens in the second stage of that, H2NO3 plus then breaks down into the electrophile, the NO2 plus, and the water. Now that's normally what they ask is you to do those equations there, but they're not asking you to do that this time. They asked you to actually show curly arrows there, so that may have been a little bit unexpected, some people. So let's see what happens there in step 1. Well, what's happened in step 1 is we have stuck another proton on. We stuck that proton on to the nitric acid, and that's obviously come off the sulfuric acid, that one there. Right, so let's see how we can think that is right. Right, so the for the oxygen to pick up a proton, we're going to have to put a lone pair on the oxygen there, and the curly arrow goes on to that hydrogen there, picks that up, and that pair of electrons in the bond goes back onto that oxygen to make that O minus there. Okay, and the oxygen's become positively charged there because it's donated a pair of electrons to, in that bond there is not a normal covalent bond, if you like, because both electrons have come from the oxygen. The hydrogen hasn't contributed anything, so that's why the oxygen is now positively charged. Okay, right, the next step, well, let's see what's happening there. Well, we can see that we have broken this bond here between the oxygen, the positive oxygen, and the NO2. Now the oxygen is no longer positive here, so that is the one which has got the electrons from that bond have gone into the oxygen. Okay, and that's going to leave the nitrogen with a positive charge on it there. So that's the unusual bit of this question. The next bit is fairly straightforward. It's just the electrophilic substitution mechanism. So we've got the electrophile here. Now what we normally show is a pair of electrons come out of the delocalized system. So we draw an arrow from the ring onto the nitrogen. A pair of electrons coming out of there, which we've lost part of the delocalized system now in this intermediate. And in the next step, that's going to reform. They've drawn the hydrogen on. Of course, there's a hydrogen on every carbon there, but we've just drawn that there because this bond is going to break. That pair of electrons in that bond is going to go back into the ring to restore the delocalized system. So they are the 4 curly arrows you need to draw there. Or the 5 curly arrows. Yeah, however many it was. Okay. Okay, off organic chemistry. Well, it's still a bit of organic, but it's about equilibrium, really. So you've got a diester. Okay, so we've got this. What we got here? We've got this. That's a diol, and we've got two molecules of ethanoic acid, and it's forming an ester at each end there. That's why it's a diester. That's the diester. But of course, we're looking at the other direction, the hydrolysis of the diester. All right. Now we've got one of these tables to fill in here. Right. Complete table 2 by deducing the amounts in terms of X of the diester, the water, and the diol. Now, they've done the code. I like to put in this third little bit here, the used up bit in my tables. Okay, so let's see what's happened. We start off with one diester, 1 mole of water, no acid and diol. By the time the reaction is finished, we have got X moles of acid. Right, we've got X moles of acid. There's the acid there. So to form 2 moles of acid, we needed to use up 2 moles of water. So we've used up X of water. That's how much we've used up there. But to form 2 moles of acid, we only need 1 mole of diester. So the diester, how much have we used up? It's X over 2, half of X. Okay, so now we have to fill in the amounts. Okay, at equilibrium, how much diester have we got left? Then we've got 1 minus X over 2. The water, we've got 1 minus X. Acid, we've got X. Now, how much diol have we got? Right, let's see for every time we make 2 acid, yeah, you only make 1 diol. So how much diol? We've got X over 2 diol. Okay, and it says, I think, so draw the structure of the diol. That's the next question. Yep, I've chopped that off, but it does actually draw the structure. So what I've drawn is, I've drawn the diester, sorry. I've drawn the diol in red, so what's going to happen is you're going to lose that water there, and you're going to lose that water there, H2O there. Let's just rub that out. Okay, so we're going to get CH3, COOH, CH2, 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 and the other bit there. Okay, so that's going to be the structure of your diester. Okay, now 5.3, a new equilibrium mixture of the substances from question is prepared at a different temperature. They always do this in case you get the X bit wrong, right? So what they're doing here, they give us the value of Kc, and we've got to, from that, work out the moles of water. So in order to do this, obviously, we're going to have to write down the expression for Kc. So Kc, I'll write it down here, is going to be equal to, now it's going to be the moles of acid, concentration of acid, concentration acid, and that's going to be squared. It's going to be the concentration of the diol, and that's not squared because we've just got 1 mole of diol being formed, divided by what the reactants we've got. We have got 1 mole of ester, and it's going to be the concentration of the water squared. Okay, now they haven't given us concentrations here, they've given us moles, and we have to realize here that moles concentration is going to be equal to the moles over the volume. And everything's in the same volume, you will see that all these volumes are going to cancel out. The reason why they do cancel out is because you've got the same number of moles of stuff on both sides of the equation. On the left-hand side here, you've got 1 mole of that, 2 water, that's 3. And on this, you've got 2 of that and 1 of that, so that's 3. If you don't have the same number of moles on both sides of the equation, the volume terms won't cancel out, and you do need to know the volume, but we don't need to know it here, we'll see. Okay, so let's put that into our Kc expression there. So what do we get? We get Kc is equal to the moles of acid is 0.452 over the volume, all squared, multiplied by how much diol have we got? We've got 0.452 moles divided by the volume of the diol, which is V. And divided by the moles of ester, diester, so that's 0.971. And let's just 0.971 over V. Multiplied by the water, H2, so the moles of water, which we don't know, over V, and that's going to be all squared because it's 2 moles of water. Okay, so what can we do there? So we are now going to multiply that out. So Kc is going to be equal to 0.452 squared over V squared times, that's not 0.452, I've done that wrong, sorry, what we got here, sorry. The acid 0.452, the diol 0.273, that should be up there, sorry. Okay, times 0.272 squared, sorry, times 0.272 and 3 over V, and divide that by 0.971 over V times H2O concentration of, moles of H2O squared over V squared. Now, you can see that that V squared is going to cancel out with that one there, and that V will cancel with that V. So we've just got those numbers. Let's multiply, and we know, so that, let's just work that out. What do we get? Get the Kc here is equal to 0.05577 over 0.971 times H2O squared. They tell us the value of Kc is 0.61 here, so let's get rid of that. I'll just rearrange that. We get H2O, moles of H2O squared is equal to 0.05577 divided by 0.971, and this 0.161 comes down at the bottom there. Do that, we get a value of 0.3, so moles H2O squared is 0.357. And take the square root of that to get the answer. And that is equal to 0.597 moles. And that is our answer to that. That's the moles of water at equilibrium is 0.597. And I'm going to leave that video there and continue with the paper in the next video.